Today morning, I was sitting in a room. There were two persons. Out of curiosity, I asked one of the persons whether it's gonna rain today or not. Immediately, one person said, "It's not going to rain today." I asked why. He was like, "No, this is the time March. Here in Bengaluru, there is a 10% probability that it will rain. There is a very less, even I wanted to say 1 to 2%. Then, after 10 minutes, they both went outside and they came back. I asked once again, "Can you tell me what is the probability that it will rain?" And then the person says it's 70%. I was like, "You said 10% 15 minutes before. Now, how you are saying 70%?" He said, "What happened is while going to take a cup of tea, we saw the dark sky. We observed something. This is their observation." He said, "You know what? I had my prior belief that there is a chance that it will rain on a particular day in the month of March here is 10%. However, today, just now I saw dark sky. So yeah, I changed it to 70%. That means here, this is a kind of Bayesian inference. Bayesian means what? Not only you depend on priors, you depend on new observation as well. It will go on updating. So the Bayesian way of inferring something or taking a decision is by knowing the posterior. Posterior not only depends on prior, but also it depends on the observation. Will not rely only on observation. If you remember, if you studied already hypothesis testing, confidence interval, or point estimation, we always relied on data. When we rely on data, there is a chance of error. So what you can do is you can take a prior idea and then on the basis of observation, you can refine the idea. That will be your posterior idea. That is one part. That is the estimation part. In two different ways, we can estimate the parameter. And then the next one is taking decision. Everything you learn in today's class, I welcome all of you to a new class today. I already gave one class. Today will be class 2 of Bayesian estimation. Let me share my screen now. I'll take you through this example. After that, I'll do this example. You will have a clear idea once you solve this problem. So what is my goal in today's class is not only to let you know how to solve this problem, but also I would like to teach you through this problem. Not only Bayesian estimation, then the next part of Bayesian is the decision, the modeling part. Both you will understand. Here, this is what we'll use. Posterior distribution is proportional to prior multiplied by likelihood. This is what we'll use, the single formula. This is shopkeeper. He sells light bulbs. And if you go by the question here, you are the subject here. You bought a box of light bulbs from a market stall a few months ago. The bulbs are all either short life bulbs with a mean life of 500 hours or long life bulbs with a mean life of 2500 hours. But you don't know because this guy, this shopkeeper, he has no idea. He says, this guy, you know what? There are two brands here. I don't know exactly which one is better one as compared to both. I don't have any idea, but these are the two brands. I know that there is a lot of difference, but unfortunately, because I'm very new to this area and I purchased both the brands and the bulbs are here. You can take and you can check yourself for some days. Then once you get the idea, you can afterwards change. This guy, Mr. Amit, he has no idea whether this one is this one is short light bulb or this one is short light bulb. No idea, absolutely. Even because there are two alternatives. Short life means what here? They've given in the question, I will show you. They've given that here average lifetime is 500 hours, 500 hours here and 2500 on an average. Okay. If you take one bulb, it will glow 2500 hours. I mean, by chance, I mean, which side you don't know. I mean, the shopkeeper, he's not sure. He's separated. That's all. There is no label here. It's not that this one is short life and this one is long life. Nothing like that. There is no way you can know because even the shopkeeper is clueless. You have no way you can know, right? So, I mean, it's a kind of chance. what I will do is, let me stick to this one. I am writing. So Mr. Amit has no idea now because the shopkeeper, even he is unable to say. So now what will happen is randomly he will choose one side. He will observe it. He has taken a sample of 5 bulbs and he used 300 hours. So according to the question, this is the sample. 300 hours, how many bulbs? 5. Let me write, this is my sample, 300, 300. If you go by the question, it's a censored sample. Censored sample in the sense, the information is not complete. Because what happened is, by now, the lifetime is more than 300 because all are doing fine now. No one stopped glowing. See, in the question, if you see it's given, in the question it's given, where we'll use one by one. This one, if you see 2500 I used already, 500 I used already, okay? And there is no way, I mean, it's prior is 50-50, nothing is given here. So 50-50 I've taken the probabilities. I'm not written, I'll write now. And then after approximately 300 hours, 300, okay, this is your sample. How many? 5 bulbs you have been using are all still going. So this one I'm using, and also this line. They are going strong, okay? Using are all still going. Assuming that the life of an individual light bulb has an exponential distribution. Now this is the modeling part, okay? We'll go to that. So the sample is 5. X1, X2, X3, X4, X5. And the sample values are equal here. And that is not 300. 300 plus I've written here because, I mean, the lifetime is not complete. Probably, if you do it after maybe some more days, this will be 450 complete lifetime. I mean, suppose, I mean, this will glow for 450 hours. This will glow for 301 hours. This could be 500 hours. This could be 800 hours. I mean, whatever it is, okay? It could be 1100 hours. You don't know. But up to 300, it's, I mean, you have some information. That's how it's a part of censoring, you can say, censored sample, okay? Whatever way, it's a sample. You got this sample. You might ask me why this kind of a sample, why not full? I will answer that also. But now we have a sample. Now that you have a sample, this one, okay, on the basis of the sample, now, see, I'm writing 50-50 here, probability. Let me write long life probability is 50%. How can I write that? Short life probability is 50%. Long life probability is 50%. This probability I will write 50%. And this probability also I will write 50%. How I will write? This way. Let me draw one distribution here. I'll write lambda here and probability lambda. This is a discrete distribution. So what they've given here, they've given that x follows, in CS2 will write this way, x given lambda follows exponential lambda. But yeah, we're not writing here now. No worries, but that is the real notation. X follows exponential lambda, the lifetime of a bulb. Now this parameter lambda has a prior distribution. Again, see, when we go to the modeling part, we'll use x, not lambda. This is very, very important for those who are studying statistics or actuarial science. Even the same for data science student, but yeah, I mean, in India, unfortunately, they take it lightly at the initial level. Most importance is given to coding part. Anyway, that's a separate issue. But you have to know conceptually, when we say prior distribution of not x, prior distribution of what? The parameter of the distribution. If you can ask, suppose there are two parameters. For example, you are using a normal distribution. So you take one as constant and one as a variable. So as I already mentioned you in the last class, unlike classical statistics, classical statistical inference, we always consider the parameter to be a constant. Parameter is a constant to be estimated from the sample. Here, parameter is not constant. Here, parameter is a random variable. That means, what is the randomness here? This is either 1 by 500, because what is given is in the question, this is given 2500. For this, it's given This is the average lifetime they've given. Okay, that means they've given 1 by lambda, 1 by lambda, 1 by 2500. Why 1 by lambda? Because just because average here is 1 by lambda. So they've given 1 by lambda for each kind of short life and long life bulbs. Here also in this case 1 by lambda is equal to 500. But this guy is clueless. That means this is uniform. The prior is uniform. Prior distribution of lambda. So you take lambda distribution. This is 0.5, 0.5. A new guy comes because you are standing there because you are now a old customer and the shopkeeper also knows you and you develop a kind of friendship. You are talking to him and the new guy comes and says, yeah, it seems you are an old customer here. Could you prescribe me which kind of bulb I should purchase from this shop? Now see, your idea will be this. We'll do that in today's class. And this is 70% of estimation. Rest 30% is modeling. So let's stick to the prior and posterior. This is posterior distribution of lambda. So what will be posterior distribution of lambda? We'll do that using that formula. 1 by 500, 1 by 2500. I remember probably this is around 92% you will get, and this one you will get around 8%. So now see, quite interesting. Now if you see this 92 here, from where you came to 92? From 50 you came to 92. From 50 you came to 8%. Now you are giving the information. You know what? If you take this kind of bulb, this one, from this side, suppose, if you take from this side, then the probability that this bulb lifetime is long life in the sense 1 by 2500. The lifetime of this bulb will be higher as compared to the other one. I mean, these will be your long life bulbs. The probability is 1 by 92. Long life in the sense mathematically lambda is 1 by 2500 and the average glowing time is 2500 hours for each bulb. That is what you can say. So this is posterior distribution of lambda. Okay. If I want to use the symbol here, symbol is this after taking the sample. Sorry. After taking the sample. So I can write something like this. Lambda given X bar. We write like this. Remember, this is notation. The X bar is sample. Okay. We write like this. Any distribution you write, suppose we started with exponential probability. So what is step 1? This will be given to you. Prior distribution of lambda. You write the distribution of lambda. I have taken a discrete distribution here. So it could be a continuous as well. In discrete also, there could be many choices. Here, there are only 2 choices. Whatever A, B, 1 by 500 we have written. 1 by 500, 1 by 2, 500, 50, 50, 0.5, 0.5. Okay. And this is prior distribution of lambda. So we write like this way, lambda, this is prior distribution of lambda. Okay. Here though it's uniform. You can write probability half, 50, 50. It's like tossing a coin. Okay. Head, tail, you can say that. And this is a uniform distribution. Okay. For posterior distribution of lambda, you have to write here in between your modeling part. I will go to modeling. One, this is over, this is 80%. So finding the posterior distribution from prior distribution is 80% of the problem. Then comes the X modeling. That is our goal. Our goal is not to find the posterior from prior. That's a part only. So now we'll stick to this. How to find posterior from prior. Lambda given X bar. Okay. This is also a discrete distribution. Only parameters will change. Only here the probabilities will change. Okay. I mean, probabilities depend on parameters. I'm not writing anything now. Just you write uniform distribution. Okay. So what we'll do is, this is the notation for prior. This is the notation for posterior. X bar, this is the notation. X under bar, this is the notation we use for the sample. Okay. So sample will be X1, x2, xn. And here if you see from prior idea, this was 50% and this changed to 80%, sorry, 8% now. And from this 50%, posterior idea now changed to 92%. That means for you, whatever is the posterior, I mean, because you already experienced, you had a prior idea 50-50, but now that you already experienced it for 300 hours and everyone is working, of course, that's a positive sign. That means you continue taking those side bulbs. Suppose this side you are taking, and you are saying this guy, because he wanted some information from you, thinking that you are the experienced guy, you are saying, please take from this side. Okay. I used already 5 bulbs and it worked fine. And till now they're glowing. So you take from this side. And if you see, if you take this side, there is a 92% chance that these are the ones, they will glow uh, for more time, because 1 by 2500 lambda means 2500 average lifetime. Okay. And this is posterior idea for you, Mr. Amit. What about Mr. Vikash? For Amit, this is posterior idea. What about Mr. Vikash? This is prior idea, because your prior idea was from the shopkeeper. Now, Vikas, his prior idea is from you. This is posterior and this is prior for him. Next time, you need not come here. B will be seen here and another guy C will come. So whatever is the posterior idea for B, that will be the prior idea for C. So it will continue, it will update. So what is the greatness of Bayesian statistics is, according to the observation, as and when it comes, you can constantly update your information. Okay, that way every prior will be updated to posterior. The refinement will happen from time to time with experience, with observation, with sample. Okay, whatever you can say. Now we'll go to the question and we'll solve this. As I already mentioned you, I'm not only doing the problem, I want to explain the concept through this problem. So let's try to solve here in this box. We'll use this formula. Posterior is prior multiplied by likelihood. All here. This is my sample. X bar, X1, X5, that is 300 plus. And here I'll find likelihood. I actually kept this for likelihood. All right, let's find here likelihood. Okay. Because this one is a truncated sample, sorry, censored sample, greater than 300 I will write. And all the time the same. So better I will write 5 times. Because X follows exponential distribution, lifetime, it's given. In case of exponential lambda, we know what is f of x and what is capital F of x. We know already, that is lambda e minus lambda x minus lambda x. And this is probability x less than or equal to x. If I find probability x greater than x, that will be e power minus lambda x. So directly we can use the result here. This will be, you put x 300, e power minus 300 lambda power 5. That will be e power minus 1500 lambda. Now we'll use this one, posterior. Again, I already mentioned you what is the posterior notation. That is probability lambda given x bar, or you write sample. If you are not comfortable with x under bar, probability given sample. Sample, this is our sample. This sample x bar. Here also if you want, I can add the sample. So probability of lambda given sample. Okay, prior is probability lambda is 1 by 500. Here probability lambda 1 by 500. I've written equality, so I'll write a constant here, constant here. Likelihood I will write likelihood here e power minus 1500 lambda. What is lambda here? 1 divided by 500. What about this? E power minus 1500 multiplied by 1 by 2500. Okay, let me write these two equations once again. I will get my posterior. Remember, sum of probabilities is always 1. It doesn't matter you add these two or you add these two. It will always be equal to 1. So from there we'll find probabilities. Let me go back. So we'll use these two equations. But before that, let me write this probability lambda. So how can you differentiate? We have to write this probability here also. We'll erase this. Probability lambda is 1 by 500 after observing the sample. Here probability that lambda is 1 by 2500 after observing the sample. Here prior, this is prior. So probability lambda is 1 by 500 after getting the sample. That will be k we don't know. K divided by 2 will write. And we'll write e power minus 3. Then the second one is probability lambda is equal to 1 divided by 2500. Given as that will be equal to k divided by 2 e power. You can cancel 5 also, minus 3 by 5. Sum of the probabilities is 1. So you can add these two, okay, and find the value of k. We'll take it. Find the value of k and posterior probabilities. Okay, total is 1 and find the value of k. K is equal to this. K is approximately equal to 3.3411. Okay. So if you solve it, k is 3.3411. 3.3411. And what about the probabilities? Let me write probabilities also. Probability that lambda is 1 by 500 given the sample, that is equal to probability that lambda is 1 by 2500 given the sample. So initially I've already taken 92%, 80%. Let's check. Yeah, 9168, 9168, 0832, 9168 and 0.0832, 0.0832. We'll go by the probabilities. Now go to this situation. We'll prescribe this guy and we'll make a arrow here now. So now we'll say these, because these are the ones this guy took. So we'll do this way. Okay, these are the better ones. Now we know, because initially there was no idea. Okay, now you go here. Now here you can say these are the long ones, long life, and these are the short life ones. Now all the time we can prescribe as long as the shopkeeper is the same and the bulbs are kept in the same place. We'll go by the probability. Okay, so we got around 92% probability. 92, here 8%. Now one part is over. Now we'll go to the second part. Acha, now let me write the distribution. What is x here? Once again I'm writing my x is, and the distribution is. Now how to estimate lambda? Because ultimately when you are saying you are modeling x, you are not modeling lambda. Okay, lambda comes in x. So you have to estimate some way, because the part is not over. What we did is the part, I mean this part we had is lambda as a prior distribution. Okay, and now we got the posterior distribution of lambda. So here here it is discrete, it could be continuous as well, whatever it is. So we got the probabilities. Okay, now that we have this, we have not estimated, even the problem is over. If you are doing the problem is over now. The solution of the problem is over. But we'll go to the next part. What is the goal of studying Bayesian statistics? Bayesian estimation part is over. You estimated already lambda here 1 by 500, 50%. It was 50%. And here posterior distribution, you write given sample 1 by 500, 1 by 2500. Now 92%, suppose 80%, whatever. Now I will say find posterior mean. Find posterior mean. It will directly find mean of the distribution. So it says mean is simple mean formula. Mean is 0.00383, 1 by 261. Okay. So it says mean of the posterior distribution is 1 by 261. Yes. So if it's 1 by 261, we'll put here. So why I've taken mean, that I will discuss. Okay. Just remember, I've taken the mean of the posterior. So what is the part 1 of this, which is the problem? That is to find posterior from prior. What is part 2 we are doing now? We want to estimate lambda. So how to estimate lambda? To estimate lambda, you see the loss. Okay. So the loss function. So what I assumed here is, my assumption here, assuming that my assumption is here loss is squared error. If I have a squared error loss function, then what I will do is I will take the mean of the posterior distribution and the estimate of the parameter. In this case, what will happen? Estimate of the parameter will be mean of the posterior distribution. So what is loss? I'll discuss just now. Okay, wait. Mean of the posterior distribution. So I've taken the mean. Mean is 1 divided by 261. So now my distribution is this. Lambda 1 divided by 261 e power minus 1 divided by 261 x. Okay. Now this is your density function you have to use. And using this density function, whatever you want, you do your wish. Okay. So remember, always we do in CS1, even in CS2, in every statistical modeling, you need to estimate the parameters. Okay. That's where all the methods come, right? Some more methods are there in CS2 as well, which you don't study in CS1. But yes, if you're a CS1 student or any statistics student, you can use those estimation methods, MLE, all those. So once you know the parameter, once you know the density function, that means you know the pattern. Okay. Once you know the pattern, the behavior, the future way, whatever way, this is modeling, this is the model, you know the model. Because if there is a parameter unknown, you don't know the model, right? So now whatever way you were doing long before, you can do the same way up to this. So now what is loss? Okay, loss will be determined from the problem. Sometimes loss is very severe. Sometimes there is a loss of 0 and 1. For example, suppose I'm using Bayesian estimation and I will predict that tomorrow there will be rain. Either there will be rain or there will be no rain. Suppose someone is tossing a coin, I'll predict head. If I get tail, or if there is a cricket match between India and some other country, say Australia, I say India will win. Suppose India will not win. Either win or not win. So my loss is 100% or 0%, 0-1 loss. I mean, in these binary cases, what will happen is you will win or you will totally lose. Okay, there is no in between. There is no compromisation here. There is no consolation. Either you win or you lose 100%, 0-1 loss. So loss, three types of losses are there. So according to the question, you have to check whether loss is 0-1 loss. This is one case. Here you take, here in this case, you take mode of what? Mode of the posterior distribution is the parameter estimate. Okay, this is what you need to take. What about loss squared error? Squared error loss means, I can give you one example. There are derivations. Okay, if you want, I have another video, I will upload it, you can watch. Derivation probably not that important, but yes, this is concept only, not the derivation. So suppose you are saying you are predicting this value. If this is less, then there is a problem. If this is more, there is a problem. Okay. Suppose I'm appointed by some property owner and I need to price the property. Okay. Suppose it's 1 crore 20 lakhs, but I will price it 1 crore 50 lakhs. There is a problem. The more is the difference, the more is the problem. Suppose I predicted 1.80. I predicted 180, but the mu, the parameter, I mean, here if you take the parameter mu, it's actually 150. I mean, ideally it should have been 150 in that area, but I estimated 180. So there is a huge loss, and you know what will happen is, because you're pricing high, slowly what will happen is people, they will not take from you. It's a competitive market, right? People will compare other properties. Suppose you predicted, using Bayesian estimation, you predicted 120 or 125 or 130, whatever. I have taken 120. Then also there is a problem, underpricing. Even it happens in actual work as well. When you are pricing, underpricing is a problem, overpricing is a problem all the time. Underpricing problem is automatically you need to shut down, because everyone will come and they will take your property, all are sold. Finally, when you see your balance sheet, you have a negative profit. I mean, you lost the business, like you will be bankrupt. So that's also a severe problem. So you go to the left, you go to the right. The more extreme you go, the more problem. So if you square it, what will happen is you are I mean, what you are doing is you are penalizing more and more as you are going to any extreme, both the extremes. The more extreme you go, the more you penalize. So if you square it, suppose 160 you predicted, 10, 10 square 100, 120, 30, 30 square. I mean, see, it's 900, right? That's square error loss. Square error means the more, whatever extreme you go, there is a problem. And whatever extent you go, there is a problem. Okay? That's square error loss. In that case, you take mean of the posterior distribution is the parameter estimate. This is mode, this is mean. And here this is 0, 1, this is squared error. I've already written. Uh, okay, loss 0, 1, loss this one. Then we'll write this way. Loss, the last one, loss is absolute error loss. Absolute means same, just take the, I mean, whatever, I mean, you go this side or this side, you penalize same way. Don't square it. Don't square it means you take the modulo. So you treat it as the loss is 30. Here also 30. So there will be loss for sure. Suppose it happened many times with me. Suppose I say someone, I mean, I taught, I mean, probably 2005 to 2015, 10 years in Delhi. So what happened is students, they used to come from far away places, from Ritala, from, you go from this side, from Faridabad, from Preet Bihar, so from all our places. So what happened is they used to come late. So if you come before also, there is another batch running. If you come after also, there is a problem. So coming before, because you have to, time is wasted anyway. 10 minutes you have to wait. And if you come late also, you lose something. So again, there is a problem. But the severity of this problem, because you have a chance that you can suppose you can go and take notes from someone, or you can ask me whatever way you could, I mean, you see the severity of this problem and that problem. So here there is no way for me, I can go for a very, I mean, high penalty. That's why I'm not squaring, just I'm taking, I mean, which side, whatever it is, whatever that way I will take. I will not square it. I will not penalize more square way. So this is a very, uh, this is a problem which is not that much crucial, okay, in terms of business value. So I'll not weigh it very high. Okay, there I will use absolute. So according to the framing of the question, you have to take one loss. Okay, so why to take mean here? Why to take mode here? That is part of the proof. I'm discussing concept again. Okay, so here parameter estimate, uh, the same parameter estimate here also. Parameter estimate will be, all right, here mode, here mean, here median. Median. Okay. So this is what you need to remember. These are three. So here, assuming that, okay, here there is an assumption, because this is not part of the problem. I wanted to explain you loss through this problem, because we have done this problem. I have taken mean of the posterior distribution. How easy it is to take the mean, because ultimately it's a distribution. Doesn't matter it's a discrete or continuous. This is continuous. Here, this is continuous, and this is discrete. Doesn't matter, because here this is the distribution of the parameter. This is the distribution of the same parameter after taking the sample. In between, we have a sample thing. And now from the posterior parameter, using that, sometimes you take mean, sometimes mode, sometimes median. You put here, you get your distribution, work is done. This is statistical modeling. Doesn't matter you are using classical way, directly depending on the sample, like you must have done in point estimation, confidence interval estimation, or this way, Bayesian, you say that the parameter is not fixed, it's random, it's a random variable, prior distribution is given, you find posterior distribution from your sample, and then use posterior distribution, see what is the loss. From the loss, you estimate using that loss, estimate the parameter of the distribution, you are done either way. So yeah, class is over for today. See you next time.